So what end behavior is the behavior of a function basically at the ends of the world, right? Normally, like up through and including algebra 2, we're always just focused on, these parts of the graph, like very close to the origin. Like the farthest we go is like x equals 10 or something, right? But there is like a whole world past that on either ends of the x-axis. So if you were to like take a spaceship and fly along the length of the x-axis, right? Like past this Earth and past the galaxy, that x-axis would never stop, right? It just keeps going and going and going. And so as you're riding along the x-axis, if you ask yourself, how is this graph behaving? And when we talk about the behavior of a graph, that term, behavior of a graph, it just means what y values is it taking on. That's what behavior of a graph is. When I say behavior of a graph, right, the responses to that are things like it's going up, it's going down, it's flattening out, and so on. All right, so that's what end behavior is. It's how a function behaves at either end of the graph. So the way we talk about it is, so as we go, further and further to the right, the x values increase so that we reach positive infinity. And then as we move to the left, the x values decrease until we reach negative infinity. So now the notation is this. As I walk towards infinity, but I don't say as I walk towards infinity, as x approaches infinity, right? And we denote that like that, x arrow infinity. So as x approaches infinity, what is the graph doing? Well, you see here that this particular graph is decreasing without end, right? So if you wanted to write that, as x approaches infinity, f of x approaches negative infinity. That's how you wrote it in algebra 2, right? But that's a handful. That's so much unnecessary notation. The calculus way of doing it, and that's how we do it here, is the limit of f of x as x approaches infinity is negative infinity. All right, this tells you the exact same information. As x approaches infinity, f of x approaches negative infinity. All right, so now on this end here, okay, the limit of f of x as x approaches negative infinity, so as you are walking towards negative infinity, what's your graph doing? It's going up infinitely, so to positive infinity. Okay? All right. And so when you talk about going to infinity, we could either go to infinity on the right side or the left side. So we say right end behavior. That's when it's limit as x approaches infinity of f of x. Okay, so you're probably going to ask, do we have to write positive infinity? Like, do we have to write plus if we're talking about positive infinity? No, it's just infinity and then negative infinity. You can write plus infinity. It's the same. And then, so left end behavior is when x is going to the negative infinities. That's how we write it. Okay? All right, so possible results for end behavior. All right, possible results. As x approaches infinity, right, the graph could be going up forever, so you could get, positive infinity or negative infinity, just like here, okay? It could be flattening out, all right, so that it equals 0 or another number. Okay, so this is when it flattens out. Okay. it could also be, it could also be undefined, but we're not going to get to that here as much, okay? So this happens more in calculus. So it's undefined when something is oscillating, right? And you don't know at infinity, is it going to be like up here, down here, in the middle, somewhere else? Okay, so that's how it's undefined. So you don't know. All right, so let's take a look at these. Yes?
An example of that be like a sine wave?
Yes, a sine, a cosine, any type of sinusoidal function. Okay? All righty, so let's take a look at the graph to describe the end behavior. All right, so the way you do it is this. Limit of f of x as x approaches infinity, limit of f of x as x approaches negative infinity. Okay, so I write that first. So now I ask myself, okay, as I walk towards positive infinity, what y value does it look like the graph is approaching? If you say it to yourself in those words, what y value does it look like the graph is approaching? Most of the time you'll come at the right answer. Okay? So what y value does it look like the graph will be approaching here? Yes?
0.
0. Now, if I walk towards negative infinity, what y value does it look like the graph is approaching?
0.
0 again. Yes, it dips below the x-axis a little bit, but then it's going to follow the x-axis. So if you zoom in here, right, it dips a little bit, but then it still flattens out. Aiden.
How about the graph underneath that? Is that a separate limit, or is that
this one?
Yeah. Is that
Okay.
a separate limit?
So this is not end behavior, because what's happening here is at x equals 1 or 2 or negative 1 or negative 2. We're concerned with as x approaches infinity.
Okay. Yeah,
You see that?
With that graph below, isn't that just keep going down?
Right. It's going down here. It's going down at x equals 2. But I don't care about that when I talk about end behavior. I don't care what's happening at x equals 2. I care about what's happening at x equals infinity. Okay? Okay? Huh? Because as I approach infinity, right? Yeah. Okay, so let's do another one. So again, limit of f of x as x approaches infinity, limit of f of x as x approaches negative infinity. So again, the language I want you to use is what y value does the graph seem to approach, not seem, but seem, as x approaches infinity. Okay? So as you walk towards x equals infinity, okay, raise your hand to answer this one. What y value does it look like the graph is approaching? Max? Yeah. Positive infinity, right? So as you're walking here, and if you have your eye on the graph, what y value does it look like the graph is approaching? Positive infinity. Okay, so now look, now I'm here. And I'm going to walk towards negative infinity. Yes.
I have a question.
Yes.
So, why isn't it free?
Well, because even though there are no arrows, because we no longer put arrows, this you just understand that, you assume that that's going up.
Then when is the other one the same with the one before? Wouldn't that also be like
But this one, like, it looks like it's flattening out here. Right? Do you see how this is like blatantly moving up in that direction? But this one, it clearly looks like it's flattening out. Right? Yeah, so if it looked like that, right? If you, yeah, there will normally, like, there won't even be a question, you know? Yeah. So now as I'm approaching negative infinity on the x-axis, and I have my eye on the graph, so, you know, look at how is the graph behaving. What is it doing? As I walk over, the graph is going further and further down, right? So what y value does it look like the graph is going to approach eventually? Negative infinity. Eventually, Okay, so in math, in calculus, there are three ways for us to come up with an answer to a question. It's graphically, algebraically, and numerically. This is the graphically part. Then we're going to learn how to do it algebraically, so that like if you're looking at, we're going to do one here as a matter of fact. All right, so we're like, you will know, you have an equation, you will know exactly what to do with it in order to come up with the end behavior. And then numerically, basically the way numerically works is you just put in numbers, you plug in numbers for x and you see what the y values are, okay? We don't do that as much. And then in AP Calc, there are more ways to do that one, okay? All right, so take a look here. It says use your graphing calculator to graph each function, identify and describe any points of discontinuity, describe the end behavior, and locate any zeros. So before we go and we graph this, take a look at this function here. First of all, what type of function is this? Rational, root, polynomial, what do we think? Yes? Polynomial. This is a polynomial function, and how do we know? Not that there are 4 terms. A polynomial can have 1 term. Yeah. It's squared, and it's, okay, so that means it's a cubic. So how do the exponents behave? What are the exponents? What values are the exponents? Right, and so how do we classify those? What types of numbers are those? Okay, are they rational, irrational, integers, whole number? These are integers, right? They're positive integers. So if the exponents of the variables are always just positive integers, it's a polynomial function. So now, let's talk about discontinuity. Are there any values of x that you are not allowed to plug in here, that it won't work for this function?
Yes.
Which one can you not plug in?
0, 1.
So you can't plug in a 1? 2. Are you not? Okay, so hang on. Are you not allowed to plug in a 1 for x here?
Oh, as in like, because it will be
right.
Never mind.
So there are no values of x for which this graph will be unreal or undefined. That means there are no discontinuities here, right? So we could just figure that out. Remember what we said last time is all polynomial functions are always continuous, right? So there are no discontinuities here. Okay. Let me give you a quick way to figure out end behavior. Okay. When you're up over at the infinities, so when x is 1,000 or 1,000,000 or 1,000,000,000, right? So suppose x is 1,000,000. How many zeros is that? 6, right? 1,000,000 squared? That's 1,000,000 times 1,000,000. 12. Okay. 1,000,000 cubed? That's 6. 18 zeros, right? So a 1 and 18 zeros basically. Okay. So I'm at x equals 1,000,000. This term is 1 and 18 zeros. This one is just 12 zeros, 1,000,000 times less, right? But it's 1,000,000 times less. So if these two were to go at it, right, at the infinities, who do you think would overpower the other one?
X cubed.
The x cubed would overpower all these other ones in a heartbeat. So when we're talking about end behavior, just end behavior, we only consider the term with the highest power. Okay? So for end behavior, look at term with highest power. Okay, so we're just going to look at x cubed. So now, if I'm on the positive end of the graph.
Wait, is this just for the numerator or also for the denominator?
I'm just doing this right now. Okay. So if I'm at the positive end of the graph, is this value going to be, this value is going to be a large number, right? When x is 1,000,000, a very large number. Will it be positive or negative though?
Positive.
Positive. So that's how I know that the end behavior will be positive infinity there. Okay? Well, right. So now if I'm at negative infinity, if x is negative 1,000,000, how much would that be? It would be negative infinity.
Wait, how would you know if the graph as it is going like that? where it just levels at a certain number.
Right, so that's the thing. If this is the one that counts, as x gets increasingly larger, x cubed is going to get increasingly larger as
So
well.
if it just stays at the same number every time, it's like a 0.
Right, exactly. Normally that will happen when you have a rational function. So let's go ahead and graph this one. So that's what the graph of this looks like. So now, did we guess correctly? There are no discontinuities. We're good on that. The end behavior on the right, yeah, it's going up forever. On the left, yeah, it's going down forever. Oh my God, so far we're like, you know, we're good on all of these. Okay, so let's find the zeros. Everybody knows how to find the zeros? Menu 6, 1. So here's 1.
And how do you do the zeros without using the graph then?
So this is the, you would factor.
Yeah. Which you can do by grouping.
Which you could do by grouping. You know what? Let's just do it.
Yeah,
Let's do it. So you have x cubed minus x squared minus 4x plus 4 equals 0. We're going to split it up here. Factor out an x squared, x minus 1, minus 4, x minus 1 equal to 0. I'm going to write the x minus 1s over to the side because that's what I'm factoring out. Then what do I have left? X squared minus 4. Right, which is x minus 2, x plus 2. So here, this gives me that x is 1 and plus or minus 2. So when I'm going to write the zeros, I either say negative 2, 0, positive 1, 0, and 2, 0, or an even better notation was what?
F of 1 equals 0.
Right, so f of negative 2 is 0, f of 1 is 0, f of 2 is 0.
Do you want us to do it the second way though?
I prefer this one, okay? Eventually I want you to go to there, like to that notation. So the sooner you start, the better. All right, so go ahead, I'll leave this to you. I'll give you like 2 minutes. Plug in this next one and fill in all the rest. When you graph, let's see. So when you graph, this is how it works, this is how it looks, and you clearly see that just like you had guessed from the equation, that there is a discontinuity at x equals 0. But what kind of discontinuity is this? It's an infinite discontinuity. So we say infinite discontinuity at x equals 0. That's how you write it. That's it. So end behavior. Right end behavior is what? Right end behavior, does it go to positive infinity? It flattens out to 0. Left end behavior, 0. Okay, and what are the zeros? So here's how, okay, so menu and 6 and 1. I'll do, there are 2 zeros, right? There is one here. Okay, so here. So we say f of negative 4.19 equals 0. And then what's the other one? Anybody find it? 1.19 equals 0. Okay?
Yeah, but when I plug those
Aiden.
is there a way to know the right enough end behavior without graphing it?
Yes, there is. We're going to go through a lot of that later on.
For now,
For now, graph it. Yeah. Yes.
Is there a way to find the zeros for that problem by like doing?
Yes, you would have to set the numerator equal to 0. We're going to do all of this by hand, trust me, by the time we're done with chapters 1 and 2.
I plugged in 1.19 and I didn't get 0.
Because it's rounded to 1.19. There is like a whole series of digits after that. Okay, determine the value of A so that f is continuous. Put a star next to this one. This is going to show up this year. It's going to show up this year again. It's going to show up again. And then it's going to show up next year multiple times. Okay? Okay. So, what does it mean to be continuous? This is a piecewise defined function. And it looks like this is being partitioned at x equals 2. Right? Okay. We're up here. There, it's being partitioned at x equals 2. Okay, so look at this one here, right? This is so what makes things continuous at x equals 2? So suppose you have one graph that goes this way. I know I'm not graphing the function that I'm given. I'm just graphing a random piecewise defined function, okay? So here is 1, and at the value at 2 is somewhere over here, right? And then the other one starts here, and it's like this. Is this a continuous function? No. Because look, there is a jump. There is a jump here, okay? In order...
Oh, you have to set them equal to each other.
Okay. In order for it to be continuous, when one leaves off, the other one needs to pick up right there. Okay? That means at x equals 2, okay, both functions must have the same value. So that means, okay, here, all right, at x equals 2, right, what's the value of this one? 2 squared plus 1 equals how much? How much does this equal at x equals 2?
5.
Well, for this purpose we do, because we're going to plug it into both, because we want both of them to end at the same value. All right? In order to make it continuous. One is going to stay open, but the other one is going to stay closed, and they're going to overlap. Okay? So at x equals 2 here, what is it? 2a. So now we set these equal to each other. We say 2a equals 5, so a equals 5 over 2. So basically what I want is the left and the right to have the same value. Okay? All right. A car rental company. Now, as Spencer said, if the question just asked you, find f of 2, then yes, you would go to this one. But for this purposes, we want them to both end at the same place. Okay. A car rental company charges a base fee of $35 to rent a car, as well as a daily fee of $15. All right? Write an equation that models the total rental fee as a function of the number of days n. So, yeah. Mm-hmm. Mm-hmm. Over n?
No.
Just 35. Just 35. It's a flat rate, so you know, just to even walk in the door, you pay 35, and then plus 15 per day. Okay? So that's that. And you've been doing this, since you were like little. As the number of days increase, what value does the cost approach? This is what we do here. As the number of days increase, and when you read the words as blah, blah, blah increase, that implies as it increases infinitely. Okay? So assume it says it increases infinitely. Okay? Now, so now think about it. As the number of days, which is n, increases and increases and increases, what's going to happen to the value of f? It's going to increase infinitely. Okay? And I know this is not a conceptually, difficult problem. The purpose of why we're doing this is for notation. So I want us to be able to write it in the proper notation. So the way we say it is, the limit of f of n as n approaches infinity is infinity. Okay? And then in words, we would say, as the number of days increase, the cost will will get infinitely larger.
Yeah, that should be.
These are, it is infinity. This is infinity. It just looked, I just wrote it quickly.